Welcome back, guys. In this mini lecture, I'd like to pause for a second and work through a few practice problems related to the phenomena that we've been exploring. So up until now, we've seen that light behaves as both a particle and a wave depending on the type of experiment that we perform. And in the course of exploring these experiments, namely the double slit experiment and these photoelectric effect phenomena, we've been introduced to a number of different equations. And I think it's a good idea to now gain some familiarity with these equations and how to use these equations to solve some practical problems. Now, as I recommend with all practice problem videos, I encourage you guys to pause after the problem is presented and try and work through the problem yourself, and then play the video and basically see how well you did. And of course, just as this little guy is being patient with somebody here who's learning mathematics, I want you to be patient with yourself if you don't get the right answer. Right? And that's all part of the learning process, but it's absolutely imperative that you spend time struggling with these problems. And trust me, if you do it enough, then you'll get it down pat. Okay, so the first relationship that I want to draw out, and we've seen a lot of them. Einstein's done a great job during the early 1900s there, coming up with a lot of very nice formula that allow us to solve a vast array of different problems. So we're going to start simple, and I wanted to look at the basic problem of calculating the wavelength of a photon with a given frequency. Okay, so I'm giving you the frequency here, and I want you to calculate the wavelength. Okay, so we've got a little equation bank up here, and basically what we need to do is look at this equation bank and figure out which equations allow us to figure out that wavelength given the frequency. And then of course, once we figure out which equation, in this case it'll be equation 1, which equation allows us to get the correct formulation, then we can plug in our values. So let's go ahead and do this. So we have a given value of nu, right, our frequency, and we need to find lambda. So we want to look for a relationship that takes us between nu and lambda. And of course, equation number 1 does just that. So we need to take equation number 1 and solve for lambda. So if we have c equals lambda nu, in order to solve for lambda, we're going to divide both sides by nu. Nu is going to cancel out, and we get a relationship here. Lambda is c over nu. C is, of course, a constant, right? A constant speed of light. And so if we plug in our values, we can plug in this constant value for the speed of light right up top, and then we can plug in our given frequency given to us in the problem, and it was given to us in units of hertz, and there's a little note here that 1 hertz is equal to 1 inverse seconds, or 1 over seconds. So solving the problem amounts to just basically carrying out this division, and you'll end up with an answer of approximately 333 meters. Okay, so the wavelength of a photon with a frequency of 9.00 times 10 to the 5th hertz is about 333 meters. Now a quick note on significant figures. Remember when we first presented c is the speed of light. This is a measured quantity. Therefore, it has a finite number of significant figures. And so we decided for the course of this problem that we didn't need to include all those different digits that I presented in the earlier video. I included only 4. Okay? And so I chose 4 deliberately because the given problem has 3, and I wanted to make sure that I didn't choose a value of c that would limit the number of significant figures for the problem, and added on a little bit of a buffer. So I included 4 sig figs up top, and so our measured value that has 3 sig figs will then be limiting, and we end up with our 3 significant figures in our final problem here. In our next problem, we're going to look at a laser pulse. So we've got a little laser, and we're going to turn it on for a second here, and we're going to shoot out some photons, and we're going to try and quantify this process. So what we're told is that we're dealing with a nitrogen gas laser, and a little pulse is coming out, and the wavelength of the photons that are coming out of this laser are 337 nanometers. And we're told that this little pulse of electrons or photons that are coming out contains a total of 3.83 millijoules of energy. And so the question we want to answer is how many photons, and we'll denote that by n, does this little laser pulse contain? And so if you look back at our set of equations up here, there's no relationship for a laser pulse. So we're going to have to do some thought to try and build that up. So you can do a quick scan there and you can convince yourself there's nothing that says laser pulse. So we need to think about what's happening here. Okay, so a laser pulse is a bunch of photons coming out. Okay, so we've got our little laser, right, shooting out photons. Okay, and what we are told is the energy of that entire pulse. What we are told is the energy of each individual photon. We know that each photon coming out is going to have an energy equal to h nu. So in this little illustration here, if we suppose that we had 3 of these little photons shooting out of the laser, then the energy of the pulse is going to be equal to 3 times h nu, or 3 times the energy of the individual photon. And so, of course, we could extend this to n photons, and we could arrive at the following equation. The energy of that pulse coming from our nitrogen laser is going to be equal to n, right, number of photons, times the energy of each individual photon. And our goal is to solve for n, so we're going to rearrange this equation then to find a relationship that relates n, number of photons, to the energy of the pulse and the energy of the individual photons themselves. Once we've done that, now all we have to do is go back and use equation 2, which tells us the relationship between the energy of a photon and the frequency or wavelength of that photon, to express our derived equation up here in terms of wavelength. So E photon, we're going to use this guy right here, plugging it in, and we're going to get n is equal to the energy of the pulse divided by hc over lambda. So of course we move our lambda up to the numerator and then go ahead and plug in all those numerical values. So you can see from that initial formula sheet, if you want to look back at that now, you can pause the video and look back. The value for the Planck's constant h here is given right here, 6.626 times 10 to the minus 34 joules times seconds. And our wavelength of that incoming, or that photon coming out of our laser, is 337 times 10 to the minus 9 meters. Minus 9 meters because we came in nanometers, and we want to make sure that our units are going to cancel at the end of the day. So we converted it to meters to match with the speed of light that we decided to use. Again, representing 4 significant figures on both of these constants here. So we've got 2.998 times 10 to the 8th meters per second. So meters cancels out nicely. Joules cancels out nicely. We have a seconds up top. 1 over seconds here, those are going to cancel out as well. So we have a unitless number, basically just counting up our photons, that comes to 6.49 times 10 to the 15th photons. Okay? And using 3 significant figures because both of the given values limited us to 3 significant figures. In this problem, we're going to explore an example involving the photoelectric effect. We are told that the work function for gold is 8.17 times 10 to the minus 19 joules. And we were asked to figure out what the threshold frequency for gold is. Now recall that threshold frequency is the minimum frequency electron or photon required to actually kick electrons out of that metal. and we denote this work function using phi. So we know phi, and we've got that corresponding energy, and we want to figure out the energy of that incoming photon. Okay, so the incoming photon must have an energy equal to phi. So if we've got an electron here coming in, we'll call that, or a photon rather, E photon, it's going to have some energy h nu. It's going to hit our gold sample, and we're trying to figure out that minimum energy required for that photon to come in, hit the metal, the gold metal, and kick out an electron. Where the work function for this gold metal is given to us. And so when that energy of the incoming photon equals the threshold frequency, then the frequency of the incoming photon equals the threshold frequency, then the corresponding energy will equal our work function. So we have a setup that looks like this. And basically all we need to do is divide both sides by this threshold frequency, and we will arrive at an expression that, sorry, not the threshold frequency, but Planck's constant, there we go, and we will arrive at an expression here where our threshold frequency is equal to that energy of the incoming photon divided by Planck's constant, and carry out this division, and we're going to be left with a value that's on the order of 1.2 times 10 to the 15th seconds. Now, let's take a second and double check this answer. How many significant figures should we be reporting here? So I want you to pause the video for a second and take a closer look at this. So I hope you'll see that Planck's constant I'm reporting here with 4 significant figures. The value for that work function that was given to us had 3, and so we should actually have 3 significant figures there. So our final answer should be 1.23 times 10 to the 15th inverse seconds. So in other words, we need to have a frequency of at least this value, 1.23 times 10 to the 15th inverse seconds, in order to be kicking electrons out of gold. Now, moving on to the second part of the same problem. Still working with gold, let's suppose that we use a light source that emits photons with a frequency of 2.0 times 10 to the 15th inverse seconds. And we want to figure out the kinetic energy of the electron ejected from the gold surface. So a quick check here, a quick comparison with the threshold frequency that we calculated on the previous slide. We found it was 1.2 times 10 to the 15th hertz inverse seconds. And so, of course, a value of 2 times 10 to the 15th is larger than that threshold frequency, so we will, in fact, see electrons being ejected. So in order to determine the energy of these electrons, we want to first go back to the very beginning, use equation 2 to determine the energy of the photon. So plugging in Planck's constant here and the frequency of the photon, we arrive at a value of about 1.3252 times 10 to the minus 18 joules. Now we're going to use equation 4 and the given value of the work function from the previous slide to determine the kinetic energy. So equation 4 tells us that the kinetic energy of that ejected electron is going to be equal to the energy of that photon, right? This is the energy coming in, at less the amount of energy required to rip that electron off of that gold surface, which is our phi. So plugging in both of these values, we've already calculated in step 1, above the energy of that incoming photon, we know the value of that work function, and therefore we can carry out the subtraction and determine the kinetic energy of that electron. Once we have that kinetic energy, we can then use the relationship between kinetic energy, mass, and velocity. Kinetic energy is 1/2 mv squared, to determine the velocity. So we solve for v, plug in our unknowns, or all these variables, solve for our unknown v, and we arrive at an answer of about 1.1 times 10 to the 6th meters per second. And notice that throughout these whole calculations, we were only have two significant figures, but I kept the remaining decimal places and held off rounding until the very end to avoid that rounding error. So here are a few examples of how to use these handful of equations involving light and wavelength properties of light and the photoelectric effect. Now would be a good time to go ahead and work through some more sample problems, and then you'll be all set for the next video where we're going to start looking at the quantum mechanical effects and quantum mechanical properties of electrons.